Okay, so we've been using this right endpoint Riemann sum to find the approximate area of the region under the graph of f of x equals x squared on 0 to 2. We did it with one rectangle, two rectangles, and four rectangles, and we did each of those manually, and quickly saw that this was going to get out of hand. So we then developed the Riemann sum formula and used summation to verify this result and convince ourselves that the Riemann sum actually was valid. And then we took it a step further and said, okay, well, let's go on and do it with 8 rectangles. And that would have been doable but annoying to do manually, so we did it with the Riemann sum and got this value. And the idea is that we're working towards a limit. The more rectangles we're using, the better our estimate of the area seems to be. Every time we double the number of rectangles, or increase it in general, we're cutting down the amount of overestimation of our function. So, looking at these values, it would be nice if we could draw a conclusion as to what they're approaching. Because if you notice, it drops quite a bit at first. It drops by 3. But then the next time it only drops a little bit. It only drops by 1.25. And then the next one it drops by, well, not even a whole number. So it's slowing down. The next time it should drop by even less, and then by even less, and then by even less. So this should be approaching a specific value, but at this point it's hard to say what that would be. For all we know, it could be approaching 3. For all we know, it could go past 3 to a lower number. For all we know, it might not even get to 3. We don't have enough conclusive evidence here, so we would need to keep going. Now, I suppose the next thing we could do is double it again and go to 16, and then to 32, and then to 64, and so on. But really, what we're looking at here is that the more rectangles we use, the better our estimate is. So why not speed up the process a little bit? Let's jump ahead and see what happens when we use 100 rectangles. Now, 100 rectangles is something you'd never want to do by hand. That's an awful large amount of rectangles. But the Riemann sum isn't going to be so bad. So let's try using 100 rectangles. Now remember, we're working with the function f of x is equal to x squared, and we're doing it on the interval 0 to 2. So, we start out as before with delta x. From that, we can also get x sub I. X sub I is a, we start at the left end point of the interval, plus delta x times I. In this case, the 0 drops off. We're left with the single term, 2 over 100i, which again, could you simplify? Yes. I'm going to leave it as it is because it's going to lead to easier calculation later on. One more step, f of x sub I. We need to actually take this expression and put it into the function. So we get 2 squared is 4. 100 squared is, well, just 100 squared. And I squared. And all of that goes into the Riemann sum formula. So again, this time I is 1 to 100 of f of x sub I excuse me. Very important. Forgot the I squared. Times delta x. What we see here are some very familiar parts of this calculation. Like, we can multiply the coefficient 4 over 100 squared times the 2 over 100. And again, in the denominator, that's just going to turn into 100 cubed. In the numerator, well, the same values that we've had every time. 4 and 2. 4 times 2 is 8. And then we have the I squared. Again, familiar process. The 8 over 100 cubed is a constant multiple that can be brought out in front. And then we have the formula of I squared when n is 100. So n times n plus 1, the next number after n, times 2n plus 1, which is actually the sum of those. Okay, now admittedly we're going to have far less cross-simplifying here than we have in the others. So we can do a little bit. It'll make it easier to type in the calculator, certainly, but we're definitely going to have to go to the calculator for this. We can, at the very least, take out one of those factors of 100 from the bottom. But besides that, we're going to have to go to a calculator. Now, the exact answer would be in fraction form. I'm going to suggest that we want to see decimal form, because the best way to see a trend of values here, to see a trend in the values, is to be able to see the decimal places so we can tell when we're locking in digits. So we turn to the calculator here, and just going to throw the whole thing in there. 8 times 101 times 201 in the top, and the bottom 100 squared times 6. And this comes out to be 2.7068. Okay, so we definitely went past 3. All right. Still not conclusive, though. I mean, are we going to 2.7? Are we going down to 2.6 or 2.5? Are we stopping somewhere else in between some of them? No real way of knowing here, except to go further. So we do that. Let's go to 1,000 rectangles. Again, if 100 was daunting, 1,000 rectangles by hand, utterly ridiculous. But here, it's just a matter of changing some of the values. N changes, certainly. But the function is still the same. The interval is still the same, which means the numerator is still 2 minus 0 is 2, but the denominator now is 1,000 instead of 100. Well, the interval still begins at 0, but delta x is no longer 2 over 100, it's now 2 over 1,000. And then times I. This is part of the reason I'm not bothering to simplify that. Leaving the denominator in this kind of form allows for some cross-simplification there, but ultimately we're going into the calculator anyway, so I don't see much need to worry too much about simplifying that. I'm just going to kind of leave it as it is. So we come down here, and again, f of x sub I is not 2 over 100 I squared, it's 2 over 1,000. 2 squared is still 4. I squared is still I squared. Don't mind Christmas decorations. And 1,000 squared is, well, 1,000 squared. So we're now doing the sum of 1,000 rectangles. So once again, we get 4 times 2 is 8, no change. But 1,000 squared times a third will give us 1,000 cubed. Still times I squared. So the only thing that's changing here are these few values. Now, of course, that's going to affect the formula for I squared, because n is now 1,000, but it's still n times the next number after n times the sum of those two numbers, all over 6, and we're still going to get that cross simplification. And it's just a matter, again, of throwing this in the calculator and seeing what it comes out with. This time I get a few more decimal places, 2.670668. Okay. At this point, we should hopefully be starting to get an idea of what this is going to. Now, in real life, not everything is going to go to a recognizable value, even when it's got decimals, even when it's whole numbers. It's not always going to go to something that's immediately recognizable. But this is an academic setting, and it's the very first one of these we're doing. So chances are pretty good it's going to something kind of recognizable. In fact, if it wasn't for all those other decimal places, I'd say it almost looks like it's going towards, well, about 2.67, 2.6, repeating. Of course, it's okay to say, I sort of think it does that, but we don't know for sure. Maybe it stops at 2.67. Maybe it goes down to 2.6. So, one step further. Well, let's kick it up a notch. Let's go to 100,000. Let's go right past 10,000. Let's just jump it up even higher. Okay. Some changes. N is now 100,000. The denominators here are, again, going to change, but the numerators remain the same. Well, even this annoyance of having to rewrite this is still better than having to rewrite the whole entire thing every single time. And at least a lot of the aspects of it are very similar from one step to the next. Just some relatively minor changes. Of course, before you go thinking that they're all going to be this easy, to be honest, how often do we do numerical limits? Certainly to introduce a concept, and there are certainly times where we may have to fall back on them, but we pretty quickly move into algebraic techniques. So chances are we're not going to see this level of repetition ever again. Okay, almost there. 8 over 100,000 cubed times 100,000 times the next number after 100,000 times adding those two together, all over 6. Once again, our one single bit of cross simplification we can do. I mean, there's other things we can do, but really at that point, why bother? It's not going to make it that much easier for us. So let's go in. Two point 666706667, and it's going to keep going after that. Now we don't see what on the calculator comes after that, but I would say this is pretty conclusive evidence to support the idea that we're going towards 2.66 repeating. Of course, we could do better. I think, though, that we're far enough along in the semester with Calc 1 to let it go at that and to move on to an algebraic technique. So let's hold this thought and table it and say that we think this is approaching 2.6 repeating, also known as 8/3. And in the next video, we'll move on to an algebraic technique that will get this value exactly in one shot instead of having to do it over and over and over again.